So, hi everyone! In this video we are going to see a simple application of physics simulation. More precisely, a set of rigid spheres falling under gravity and colliding together. The basic setup of such scene is quite simple, and it's a pure particle-based simulation that you can build easily in your lab class. We will also see at the end that if we want to go into the details and actually handle really correctly all the collisions, then the problem will become much harder. So let's start first with the modelization of the system. So we have a set of particles corresponding to hard spheres defined by their center pi and radius ri. These spheres can collide with the surrounding obstacles and can also collide with each other. The particles are also associated to velocity, the vi, a constant mass mi, and we know the initial conditions. There is only a single force per particle, which is the weight, Fi, which is equals to the mass mi times j, and the collision will be handled using impulses. So the temporal evolution of the particle is very simple. Actually, the velocity is the derivative of the pi, and the derivative of the velocity is the gravity constant. Usually we will also add a drag force acting as a force opposite to the current velocity of the sphere, and we can solve numerically the system using a standard iterative scheme. So the interesting part of the simulation is actually to handle the collision. So the first and simplest collision is the one between a sphere and a plane. One way to describe a plane is to parameterize it with a point that can be in arbitrary position inside the plane, and the unit normal of this plane that we call n. It's not the minimal number of degrees of freedom for defining a plane, but it's a convenient representation to perform geometric computation. We will also suppose that this plane is oriented, meaning that the positive direction of its normal is the allowed space, while the negative part is supposed to be inside some wall, and so we should not have spheres in this space. So we can characterize that a point P belongs to a plane if P minus A scalar the normal n is equals to 0. And using this relation, we can characterize if a sphere is above the plane when pi minus a dot n is greater than the radius ri, and otherwise it means that the sphere is in collision or inside this plane. So this relation gives us a way to very simply detect a collision. Basically, we can loop over all the vertices, we compute the dot product between p of I minus a and the normal n. And depending on the sign of this value, we know if we have a collision or not. Then the next question is, what should I do when a collision is detected? So using our sphere model, we would like the sphere to bounce out of the plane. So what can I do to model that? And the trivial idea is to adapt the velocity of the particle. So let us suppose that the particle is in contact with the plane. So we have pi minus a scalar n, which is equals to the radius ri. The response of the collision is actually an adaptation of the velocity. As the sphere should bounce out of the plane, we can decompose the velocity into two local components. A component along the normal direction, that we call v orthogonal, and this component should be negated after the impact. And a component which is parallel to the plane, that we call v parallel, and this component should remain the same after the impact. So expressing v orthogonal is easy. We just project the velocity v on the normal direction, so v scalar n, and multiply it by the vector n. So we shouldn't forget that this component is a vector and it should be aligned with n. And it's also important to remember that n is of unit norm in this formulation. And to express v parallel, we simply take v and remove the v orthogonal component. Then the new velocity after impact can be computed as the new v is equals to v parallel minus v orthogonal. So we negate the orthogonal component to model the bouncing effect. Of course, if we simply do that, the sphere will bounce without losing energy. So if we want to model some kind of loss of energy, then we can add some restitution or attenuation coefficient, and possibly add different coefficient for the parallel and orthogonal component, which will guide how much speed the sphere is losing after the impact. And then it seems that we have an algorithm able to make the sphere bounce. So we can code it, throwing some sphere in a cube, and we can look at the result. And this is the type of result that we obtain. So the sphere actually sinking inside the ground instead of staying on it. So what went wrong with our algorithm? What did we actually miss? So actually, we should come back and remember that we did all our analysis of velocity modification, supposing that the sphere was actually in contact with the plane. But we are using a numerical integration along finite time steps. And exact contact of our sphere with the plane will actually never happen with time discretization. Actually, once you have detected the collision, your sphere is already inside the wall. Then you inverse the direction of the velocity, but at some point, your sphere will not bounce high enough and may be still in collision at the next time step, which means that the velocity is inverted again and then goes even more down. So, of course, one way to improve the result is to check that you don't reverse the velocity when you are still under the plane. But in any case, the gravity will always have a tendency to push you downward, and if you have other constraint happening, the sphere may still end up below the ground. So if you want to really avoid the possibility of the sphere to pass through the wall, then we can also modify its position. And there is actually several ways to compute the new position, such that the sphere doesn't intersect with the plane. The first possibility, which is the most simple to set up with even complex geometry, is to displace the object out of collision as straight as possible. So in the case of a sphere and the plane, we can move the sphere in the direction of the normal of the plane, such that the new sphere position is in contact or just above contact. So this displacement is straightforward to implement for sphere and plane, but of course this is violating the physics of the phenomenon. We are basically applying a sudden teleportation of the sphere. So the second possibility is to try to find a more correct position of the sphere, typically in doing a search along the straight line between the current position and the previous one, and then find a more plausible position where the sphere actually intersected the plane. So this approach is a little bit more complex to set up than the simple projection, but leads to a more correct position. The last and the more correct way to deal with such response is actually to try to find the actual time of the collision that happened between the time step. Once this intersection time is found, as well as the contact position, then the bouncing effect can be applied and the new position can be computed from the remaining time in this time step. So this approach is called the continuous collision detection, or CCD in short, and it's more correct with respect to the physical phenomenon. The bouncing effect is took into account along the displacement of the sphere. But the computation of this approach is, however, more costly, as we need for each contact to find the precise contact time, typically using a binary search approach. And this is finally the result we obtain when we apply the simplest response, which is the direct projection on the plane. So we treated the case of collision between a sphere and the surrounding planes, but the spheres themselves can collide together. So first, how can we detect the collision between two spheres? If we have a sphere at position P1 with radius R1 and another one at position P2 with radius R2, they are in collision if the distance between P1 and P2 is less than R1 plus R2. So detecting the collision is actually very simple. Now let's suppose that the sphere have velocity v1 and v2 before the collision. What happened with their respective velocities after? So this is actually not as straightforward than in the case of the collision with a plane. Obviously, the spheres are going to move away of each other, and the separating plane between the two spheres are going to play a role. Here, a kind of intuitive answer would be to say that we project the speed along the component of this separating plane and invert the direction of v1 and v2 with respect to this plane. But actually, this is not exactly what will happen. And of course, the mass of the particle should play a role into the response. So, to find the actual effect we should apply, we go back to the notion of impulse. We remind that the impulse J is the integral of a force over time. And an impulse is able to model a sudden change of velocity, typically happening during a collision. For a particle with constant mass, the integral of the force between t1 and t2 is equal to the mass times the difference between the velocity at time t2 and t1. So for an impact, we have the new velocity, which is equal to the whole velocity plus the impulse divided by m. So let's go back to our spheres in collision. First, we can note that the impulse will take place orthogonally to the separating plane. Indeed, if we look at the phenomenon, the force taking place during the collision are the reaction force of the sphere. These reaction forces are only along the direction which is orthogonal to the separating plane. Note that if we were considering actually rigid bodies with friction and a given angular velocity, the problem would be more complex. But in the case of particles, there is not the notion of rotation of the particles. So as the reaction forces are only taking place in the direction defined by the vector p1 to p2, the impulse will also be oriented along this direction. So now we have to find the magnitude of this impulse, J. Or more precisely, the impulse J1 and the impulse J2 acting on the sphere 1 and 2. So now let's consider the two spheres as a unique system. If there is no other collisions, it's an isolated system before and after the contact. And as an isolated system, its linear momentum is preserved. So if we write the preservation of the linear momentum, we have m1 v1 plus m2 v2 that has to be equal to m1 times the new speed v1 plus m2 v2 new. Once we rearrange the terms, we see that the impulse J1 and J2 are actually equals and opposed in direction. So basically, independently of the mass, the particle will experiment the same impulse, which is kind of a simple reinterpretation of the notion of action-reaction. Now, to find the actual value of the impulse, we need to have more assumptions about the type of collision. So the most common type of collision is the one called elastic collision. Or this is the model of the hard spheres, which lead to the bouncing of the spheres. So this model actually assumes that there is no loss of energy and that the total kinetic energy of the system is preserved during the contact. As a side note, another model could be the inelastic collision, that leads to the fact that the elements stick together after the collision instead of bouncing on each other. And in this case, the kinematic energy would not be conserved. But let's go back to the elastic collision. And then we can write the preservation of the kinematic energy. So we have 0.5 m1 times v1 squared plus 0.5 m2 times v2 squared. That has to be equal to half of m1, the new v1 squared, plus 0.5 m2 times the new v2 squared. And again, we can rearrange the terms and integrate the impulse, and then we get the final expression that says that the impulse, the magnitude of the impulse, is given by 2 times m1 m2 divided by m1 plus m2, which is called the reduced mass of the system, times the dot product between v2 minus v1 scalar u. which is the relative velocity orthogonal to the separating plane. So we can finally express the new velocity of the particles, and we see that the influence of the mass is taken into account thanks to this notion of reduced mass and the relative velocity. Otherwise, the formula is not trivial. The things get interesting to interpret if we consider that the particles have the same mass. Then we end up with the relation that the new velocity v1 is equals to v1 parallel plus v2 orthogonal. And the new velocity v2 is v2 parallel plus v1 orthogonal. So it means that we have actually switched the orthogonal component of the velocity between the sphere 1 and the sphere 2. So we should not inverse the orientation of our own velocity to create the bouncing effect, but we should actually switch the orthogonal velocity. And although it may look unintuitive in the first place, this is actually what we can see in many situations, such as these two spheres. Every time they collide, the one with the greatest speed actually passes it to the other until they collide again, and so on. And the case of velocity inversion would actually take place if we were considering a sphere colliding to another very massive and static sphere. And finally, of course, we can consider the restitution coefficient to model a loss of velocity after the impact, and adapt such coefficient in the parallel and orthogonal direction. So as a summary, the algorithm to model this stack of falling spheres together is the following. So we detect pairwise collision between the spheres. Then if the collision has a high relative speed, we apply the bouncing effect using the elastic collision. Otherwise, if the collision has a small relative speed, we can simply consider a friction rather than a bouncing. This allows to limit the jittering that can arise when a lot of spheres are colliding. And finally, we shouldn't forget that the position of the sphere themselves should be updated in projecting them on the contact surface to avoid that collision remains after the update of their velocity. And there is one thing we haven't discussed yet, which is the multiple collisions. So far, we only described how we can deal with pairwise collision, assuming that the spheres are free to move in other directions. But when we have lots of spheres, things can become more complex. When we correct two particles that collide each other and move them to their contact surface, then correcting their position may lead to the generation of new collisions with other particles. And basically correcting each pair of colliding spheres, one after the other, doesn't ensure that you will end up with a global state that is free of collisions. Also, the order in which you treat the collision have an impact on the result. And technically, you have a better chance to preserve in the final result the collision that you treated last than the first one. So in the case of the example of the lab class, you will get, for instance, a better visual result in treating first the collision between the spheres, and then at last the collision between the sphere and the plane. Like that, you won't see the sphere going out of the boundary of the box. While you may have lots of intersection in the middle of the spheres together, but it won't be such visible. While if you start first with the sphere and plane, and after you treat the collision between the spheres, you may push some sphere below the ground, and you will immediately see that something looks wrong. When such problem appears, you can slightly improve the results in reducing the time step, for instance, or iterating several times over the collision handling. But doing that will only limit the problem, and it still doesn't avoid collision globally. So if you want to reach for a correct solution in all cases, then the problem is more complex. You need necessarily a global approach, and you cannot only deal with pairwise collision. For instance, the figure shown in the right is actually a very complex problem to tackle. All the spheres can only separate and move in the direction they can, and the shock of the particle should propagate through multiple spheres, and the symmetry of the system should be preserved. So one possibility is to compute a contact graph of elements that are in contact. Then When an element collides with this pile of elements, the shock can be propagated along them until reaching some movable element. Such approach can be adapted when dealing typically with elements that are locally piled up, and then these piles can be handled separately as some kind of individual elements. Or another and more general approach is to express the system of impulses to apply as a global system under constraints. Actually, the impulse should separate the colliding elements away, so this is an inequality constraint. And another set of constraints is the preservation of the momentum of colliding elements, and possibly the preservation or dissipation of energy. So the formulation as inequality makes the search for a solution more complex than a simple system. A common approach is the use of linear complementarity program, LCP, to convert it as an equality constraint, and then use iterative solver such as Gauss-Seidel or Jacobi to solve the constraints. And you can find some early literature on such approach, like the one in 1988. But as you can see, there is still research in the recent years on this problem, like the publication from 2017 that tries to find a condition to be satisfied to really simulate correctly these multiple collisions using iterative solvers.